Alright, hey guys, welcome back. So we are still in the middle of talking about regression. And so we had just finished up on page 5 of our note packet, just talking about like predictions, talking about residuals. Prediction regression usually isn't really too bad. You just throw in whatever number for x that you're interested in predicting for, and you solve for your prediction. Now we're going to take a little bit of a diversion and spend a video talking about some more theoretical aspects. And so this will be as theoretical as we get, because this is, again, intro to like applied statistics, not theoretical statistics. But we are still going to cover where this fitted regression line comes from. So we kind of talked about like this idea of best fit earlier in the handout at the bottom of page 3. And so we had just said we want points as close as possible to the line. And now we're going to cover kind of a more formal definition of what that means. So to do that, let's just say we have this simple example where we just have 4 different data points and we fit these 2 candidate lines. So one of the lines is solid, the other line is dashed. Before we do anything, we should kind of note that that one of these lines seems to fit better than the other. So take a second just to think about, okay, well, which line fits better, and which line would I expect to kind of have a better fit. And so I think most of us would agree that this solid line seems to fit the points better. The dashed line doesn't really fit the points quite as well. How we're going to measure fit though, we don't just want this kind of abstract definition. We want like a single number to measure fit of the lines. And the most common way to do that is to use this, which is called the sum of squared residuals. So remember, a residual, so like the first residual, is going to be the first response value minus what's predicted based on our model. We could repeat that for every single point in our data set, square them all, and then add them all up. And so I think it's a little bit easier just to see what this looks like in practice. And so let's start by finding the sum of squared residuals for this solid line. And so for this solid line, what I'm going to do is I want to find the residual for this first point first. And so the residual for this first point, using our little formula for residual, I'm going to take the observed response value, which looks like it's about 1/2 or 0.5. I'm going to subtract what's predicted based on our solid line. So that looks like the predicted is about 1. I'm going to square that. And then I'm going to repeat that for the other 3 points. So the second point looks like it has an observed response of 1.5. The predicted based on our model looks like it's predicted to be 2. I'll square that. I'll repeat that for this third point. And then I'll repeat that for this last point. If you do all that, you should wind up with a sum of squared residuals of 1. So we said that the best line is going to minimize this sum of squared residuals. And so as we're doing this for the dashed line, we would expect the sum of squared residuals to then be larger. So let's see if that's the case. So I'm going to take my first observed response, which is again 0.5. I'm going to subtract the fitted based on this dashed line, which looks like about 2. I'm going to square that. And then I'm just going to repeat that process for these other 3 points. So the second point, the third point, and the fourth point. If you do all that, you should wind up with 6.5. And so we are actually seeing that which line has the smaller sum of squared residuals, the solid line. And this makes sense because a smaller sum of squared residuals means a better fit, since a smaller sum of squared residuals means that the errors are in general smaller. And so take a minute to ask yourself, okay, then is that solid line, so the line with the sum of squared residuals equal to 1, is that the best possible fit line? Okay, did you think about it? Okay, so not necessarily. There could be a line with an even smaller sum of squared residuals. So what do we need to find this line that has the smallest sum of squared residuals? Well, there's actually, for this simple kind of linear regression case, there is like an algebraic formula to find the slope and to find the intercept. We're not going to do that. We're just going to note that we need some sort of statistical software to find the best line. And so since we're not ending up using R for this remote learning session, we're just going to learn how to read statistical software output. The benefit of this is that really almost any statistical software that you use is going to have output that looks super similar. So if we learn how to read output from R, then you should be good for most other statistical software as well. As always, let me know if you have any questions about any of this stuff.